Hello, now we are at problem number 9, the second last problem. It's a long one, so let's read it together. We've got an ant which walks along in the x-axis by taking a sequence of steps of length 1. Some or none of these steps are in a positive x direction. Some, none, or all of these steps are in the negative x direction. Alright, so basically the ant is walking along the number line, and every time it walks it moves to the neighboring whole number. It might be the previous one, it might be the next one. You have a kind of absolute freedom over whether to move to the right, move to the next number, or to the previous one, to the left. You have total freedom over that. Just that you need to end up at a given number. You see, the ant begins at, the origin x is 0, takes a total of n steps, and ends at x equals d, ends at number d. And for each sequence, let c be the number of times that the ant changes direction. All right. So let's start with the subproblem A. It says that determine the number of different sequences of steps for which n is 9 and d is 5. All right. So as we said, we've got absolute freedom over whether to move to the left or to the right at every step, as long as we can end up at the given location. In this case, it is 5. So basically, we start with 0 and end up with 5. After 9 moves, let's write it down. After 9 moves, we end up at number 5. All right. So how many moves? If we start at 0, end up at 5 after 9 moves. So it's a 7 towards the right and 2 towards the left. Right. 7 plus 2 is 9. 7 minus 2 is 5. So it works. Okay. So basically, we have 9 moves. 9 moves, and out of the 9 moves, 2 should be towards the left. Whichever 2 would work. So it's 2 out of 9. This should be 9 times 8. Take 2 objects from 9 different objects. We have a 9 times 8 divided by 2 times 1, which is a 36 different ways. So we have basically 36 different sequences, and the answer to the first subproblem to A is a 36. Here we go. It's not quite a hard one. And now let's move on to the second part. And suppose that now n is 9 and d is 3. Okay, the number changed a bit, and we have to determine the number of sequences for which c is even. Okay, again, what is c? Let's have a look. Okay, let c be the number of times that the ant changes direction. Okay, so basically, in this subproblem, we are not looking for the total number of possible sequences. We want those sequences where the number of changes is even. That the ant has changed its direction for an even number of times. Okay, what does that mean? Maybe let's kind of visualize this better. Visualize this. So 9 moves. Again, it's 9 moves. End up at 3. So it is a 6-3 story. 6R and 3L. Okay, 6-3. So let's draw a 6 times 3 rectangle, a grid. 1, 2, 3, 1, 2. Okay, here we go. So the ant, which at the end is kind of not the ant. The ant is moving along the number line. I mean my mind or whatever. We would start from here and end up at this point. We can move to the top, move upwards or to the right, and the total number of changes should be even. Meaning, let's see, if I do something like that, this is not good, right? This is just one change of direction, and this is odd. And what's even? Let's see. Okay, if it looks like this, even, good. Okay, or maybe we make our first move upwards and then to the right and then upwards again. This is even 2, right? 2 of them. Let's try something with 4. 1, 2, 3, 4, right? 1, 2, 3, 4. Okay, this is even, okay? Or another 4 maybe. 1, 2, 3, 1, 2, 3, 4. Okay, that's a 4, that's even. So all these kind of routes, all these kind of paths satisfy. And what's in common with them? Okay, it's easy to tell. The first move, the very first move, and the very last move has to be the same. If you start with moving to the right, you should end up with moving to the right. If you start with moving upwards, you should end up with moving upwards, okay? The very first move and the very last move should be the same, and that's it. As for the second move, it doesn't matter. For example, in this diagram, in this graph, if the first move is towards the right, it doesn't matter if the second move is towards the upwards or towards the right, but the very last move should be towards the right. The first move and the last move should be exactly the same. Okay. So basically that is what I'm talking about. So this one basically comes down to, can be break down to two sub-problems here. Okay, we need some more space here. Problem number 1, we're gonna take the first move towards the right and the last move towards the right, and what's left is what's remaining is something in the middle. That should be something like that, all right? 1, 2, okay. Here's what we've got here. We're gonna start from here and end up at here, taking whatever route you like, because the very first move is like that and the very last move is like that. This is enough to guarantee that the total number of changes is even. And also we can take the first move upwards and the last move upwards, and what is right now in the middle is this part. So we've got, it's basically 6 times 1 thing. It's relatively easier. The first move is like that, the last move is like that. So the even number thing is already guaranteed. We don't have to worry about that. And the answer should be the number over here plus the number over here, right? It's a kind of a recursive thing. And there's no repetition between these two, because anyway, the first move are different. The first moves are different. So they are two, I would say, two separate categories. All right. So let's do it quickly. 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 3. Okay. You can also use this kind of a way, but whatever way works, because it's not a huge number. 20, 35 over here. Okay, 35 for this part, and here 1, 1, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7. We've got 7 over here, so the answer should be 35 plus 7. That is 42. We've got 42 different sequences for which C is even. The number of turns is even. All right, and this is the solution to problem B. Okay, now we are finally at problem C. Determine the number of pairs Dn of integers with m between 1 and 2024, and D is a non-active, for which C is even for exactly half of the sequences of n steps that end at x equals D. Okay, and at D. So again, n moves end up at D, and C is even for exactly half of the sequences. Okay, meaning, okay, basically it's like that. If we got something like that, okay, again, so say it is something like that, and as we know that this would be give a even number, something like this or something like that would give an even number of turns, and in that case we would count it towards C, and half of the total sequences should be C. Okay, half of the total sequences should be C. So let's see. If say we've got a diagram like that, and this length is x and this width is y. Let's say x is no less than y. All right. And let's say, okay, d could be 0, so x could be y. Okay, never mind. And what is x? So basically x is x plus d divided by 2. And later we might need to use this. But for now, let's just do with x and y, which could be easier. And the total number of sequences, okay, no matter whether c is even or odd, the total number of sequences should be x plus y. And then you take x or y. Let's just use y is a small number, maybe. Okay, I don't see a difference, but okay, take y out of x plus y. So this is the total number of sequences, and half of it should be the sequences where c is even. Okay, so again, we've got something like this, right? Something in the middle and something in the middle, as we did in the previous sub-problem. So, okay, so what's this? I mean, this one right in the middle, all right? And the length this time is x minus 2. But the width is the width or the height is the same. It's still y. So the total would be x plus y minus 2, right? X minus 2 plus y, or the other way, x plus y minus 2. That's the same thing. And take let's say it's x minus 2 out of x plus y minus 2. All right. And also this this flattened one. Let's see, this should be, the total should be, see, the length is still x, and how about width is y minus 2. So again, x plus y minus 2. And as for the number to be taken out, it's y minus 2. Okay, okay, we've got kind of a symmetry here. And this is what we have. This basically means that half of the sequences, half of the total number of sequences, are those sequences where c is even, or the number of turns is even. Okay, and let's see if we can derive anything from this. Okay, it might take some time. Let's see it. A half, and what is this? Okay, by definition, it's factorial divided by x plus y minus y. This is just x, so x factorial. So you see y factorial. This basically makes no difference. I mean, even if I wrote x under here. And this should be x plus y minus 2 factorial divided by x minus 2 factorial, and it's a y factorial because y is a x plus y minus 2 plus x minus 2. Okay, and for this part, for the same reason, and okay, I just do it quickly. It's x factorial and y minus 2 factorial. All right, it's not quite hard to deal with because something can be removed at the same time. For example, this part and this part can be removed from the top. It's one something. And let's just do it step by step and copy the denominator for now. And on the top, 2x factorial, y factorial. On the top, this part is gone. So we've got x plus y and x plus y minus 1. And that's everything we've got here right on top. And what about the denominator? What about the base? Okay, let's just do times x factorial and y factorial. So this is a 2, x plus y minus 1. And on the other hand, we've got okay, these are gone. So we've got x. I mean, no, I'm sorry about that. X and x minus 1, and plus y and y minus 1, right? On the numerator, they are on the top. Okay, and that's it. Need to break up the brackets. Here it is, okay, it's a minus 1. So it is x squared plus y squared plus 2xy minus x minus y, all right? 2 moves over here. It is 2 times x squared plus y squared minus x and minus y, all right? This is what we've got here. So 2x squared plus y squared and x squared plus y squared. And this is x squared plus y squared. This is a minus y minus x. This is a minus 2x minus 2y. So over here it is 2xy plus x and plus y. Okay, and then let's move this over there to get some square. It's xy equals x minus y squared. Okay, it's something like that. And for now, what can we do? Okay, let's go back to this. Okay, by definition, what is x? Okay, after all, x is half n plus d. What is y? Y is half n minus d over here. So basically, what we've got here is that n is d squared. Yes, that's the very relationship we are looking for. N is d squared. If n is d squared, and we can go all the way back, and this identity would be true. So if n is d squared, and we've got this identity. In most cases, I would say in most cases, because to derive something like this, we used a kind of a recursive way. We have to delete the top row, the bottom row, or maybe the left column and the right column. But in some base cases, we've got only like 1 and 2, one row or just one column, and we cannot go any way back, any further back. So that might be a different story. We have to be careful with that. But and generally speaking, I would say this identity, this relationship would it should be enough for us. So let's say n is d squared is all we need. And what else do we have? Okay. Let's see, we've got a range thing is between 1 and 2024. So n is d squared and n is between 1 and 2024. So meaning, and of course they are integers, so n is a squared number, perfect square. So what square is just above, just below 2024? 40, let's try 45. 45 times 45, 25, and this is 180. Oh, 2025 is just over. So, okay, easily, it's 44. So, n could be 1 squared, 2 squared, 3 squared, all the way to 44 squared, but not 45 squared. But as I said, we have to double check, especially on the base cases, okay? So let's just check this one and this one, because I think this number is big enough. So if n is 1 and d is 1, okay, here d is 2 and And if n is 1 and d is 1, meaning after one move, we should be at 1 on the number line, and there's actually only one way. Okay, so if there's only one way, we cannot say something like exactly half of the sequences, because half of 1 is not even an integer. And so this is not, this doesn't actually satisfy, as I said, base cases could be dangerous. We have to kind of remove this. Okay, this should not be counted. Okay, how about this one? N and D. N is 4, is D is 2. It's a 3-1 thing. Okay, 3-1 thing is not good because, you see, it's a one row. It's a one row structure. And how many different sequences in total? 1, 1, 1, 1, 1, 2, 3, 4. 4 sequences in total, right? And how many sequences gives the C as an even number? Let's see. If you move this way, it's odd, right? It's just 1 turn. It doesn't satisfy. If you do this, 1, 2, okay, there is 1. And if you do this, 2, 1, and there's another 1. And if you do this one doesn't satisfy. This one satisfies. This one satisfies. So it is 2 out of 4. It is good enough. It is good enough. Although it is a one row thing, it still works. So 2 out of 4. This is just a half of it. This is just a half of it. So this one works. This case works. And from this point on, we do not have any one row thing or one column thing, so everything should be safe. So these cases should be safe. This is okay, but this one has to be deleted. This one has to be removed. We do not count this one. So in total, it is 44 minus 1. 44 minus 1, the answer is 43. We've got 43 different pairs of D and N, and that is basically 2 dn. Okay, in the order of dn, there's 2 to the 2 and the 2 squared, 3 and 3 squared, all the way to 44 and 44 squared. And okay, within the range of 1 and 2024 in terms of n. And so anyway, 43 is the answer to this problem.